friends, my name is Tushar and today we are going to talk about Floyd-Warshall all-pair shortest path algorithm. So you're given a directed or undirected graph. Floyd-Warshall algorithm is used to find the minimum distance between all pairs of vertices in this graph. Floyd-Warshall algorithm is a dynamic programming algorithm. It works with negative weight edges on the graph, and with little variation it can also detect negative weight cycle in the graph. There are many applications of Floyd-Warshall algorithm like Clean's algorithm or transitive closure or widest path in the graph. So next, let's see how this algorithm works. So we are going to apply Floyd-Warshall on this directed graph here. First thing we do is we take two-dimensional matrices. The size of their matrix is going to be same as the total number of vertices. So here we have total 4 vertices, so the size will be 4 cross 4. Then we go through all the edges and put their value in this distance matrix. So distance matrix is going to store the minimum distance found so far between two vertices. So for the edges, if there is say there is an edge between 0 to 2 and this distance is 6, so 0 to 2 will be 6. Similarly, there is an edge 1 to 2 and distance is minus 2, so 1 to 2 will be minus 2. Also, this path is going to be used to regenerate the minimum distance path between two vertices. So initially, if there is a path between say 0 to 2, so then 0 to 2, so we are going to put 0 here. So the start of the edge. And so there is a path between 1 to 2, so we are going to put 1 here. And for all the paths which doesn't exist, we are going to put infinities, and 0 to 0, 1 to 1, 2 to 2 and 3 to 3 is going to be 0. And here I am just going to put n, indicating that there is no path available right now between two vertices. So then we are going to have 3 for loops, k going from 0 to 2, 0 to 3, I going from 0 to 3 and j going from 0 to 3, and every time we are going to check this. If d of ij is greater than d of ik plus d of kj, then distance of ij will become distance of ik plus distance of kj. So basically checking for every pair of vertices, do we get a shorter distance by going through k, and k ranges from 0 to 3. So basically, in effect, we are doing 3 for loops, and the total number of operations will be 4 into 4 into 4, which is 64. So we are going to do this check 64 times. So to save on time, I have pre-written the 16 of those checks. So basically for k is equal to 0, I equal to 0, I equal to 1, I equal to 2 and I equal to 3, and j is 0, 1, 2, 3. So we are going to quickly do the checks and update this matrix if we satisfy this condition. So let's run through this example very quickly. Initially k is 0. So what we are checking is for every pair of vertices is going to go through k, which is vertex 0, going to give a shorter distance or not. So we have in total 16 such combinations because we have 4 vertices in this graph. So for every combinations we are going to check is going through k0, vertex 0, going to give a shorter distance or not. So this format here is dij is greater than dik plus kj. So basically we are doing this check and seeing if dij is greater than dik plus kj. If yes, then we update the distance to be that distance. So 0 is not going to be greater than 0 plus 0. So this is not true. 3 is not going to be greater than 0 plus 3. So this is not true. 6 is not going to be greater than 0 plus 6. So this is not true, and this is not true. So far going through 0 vertex has not given a shorter distance. So once we are done iterating through all the values of j, we go here and increment our I by 1. So k continues to be 0, I increments by 1, and then again we are going to go through all the values of j. So infinity is greater than infinity plus 0, it's not. 0 is greater than infinity plus 3, it's not. Minus 2 is minus 2 greater than infinity plus 6, it's not. Is infinity greater than infinity plus 15, it's not. So now again we increment our I by 1 more, so I becomes 2, k continues to be 0, and again we are going to set our let's set our j from 0 to 3. So is ij greater than ik plus kj? So is infinity greater than infinity plus 0? No. Is 2, 1 ij greater than kj plus ik plus kj? So again no. Is 2, 2 greater than 2, 0 plus 0, 2? So 0 is not greater than infinity plus 6, and 2 is not greater than infinity plus 15. So finally our I becomes 3, k continues to be 0, and again j is going to go from 0 to 3. Is 1 greater than 1 plus 0? No. Is infinity greater than 1 plus 3? Yes, infinity is greater than 1 plus 3. So what we are going to do is we are going to go to this place 3, 1. So 3, 1 and set this distance to be 1 plus 3, 4. So basically saying dij is equal to dikj plus dkj. And in here I am going to set path ij is equal to path kj. So 3, 0 will become kj, so 0, 1. So whatever the value here, it becomes here. So what happened was, before k was introduced, k0 was introduced, there was no path between 3 to 1, which is why that value here was infinity. This value here was infinity. But now going through vertex 0, we have a path of length 4, 1 plus 3, 4, which is why the new distance between 3 to 1 is 4. And we are also going to indicate that we are going to go via 0, which is why this value here is 0. Again, coming back here, is infinity greater than 1 plus 6? Yes. So again, we are going to go to 3, 2, update this distance to 7. And then we are going to go to 3, 2, update this distance to, update this path to 0, because we are going via 0. And again, this condition was satisfied. And as you can see, before 0 was there, there was no path between 3 to 2. But once 0 got introduced, there is a path going from 3 to 2 via this path, so 1 plus 6, which is 7. And we are indicating that we are reaching through 0. Finally, is 0 greater than 1 plus 15? No, so this is not true. So this is all the iterations for k equal to 0. Next, we are going to increment our k to 1 and see if we can find a better path going via vertex 1. So now our k is 1 and I've updated all the values accordingly. So we are still looking for dij, is it greater than dik plus kj? So is 0 greater than 3 plus infinity? No. Is 3 greater than 3 plus 0? No. Is 6 greater than 3 minus 2? Yes, 6 is greater than 1. So what we're going to do is we're going to go to 0 to 2 and update this value to be 3 minus 2, which is 1. And we're going to go to this path and set this value to be whatever is the value at path 1, 2. So path 1, 2 is 1. So this value becomes 1. So basically what happened was, now that we are going through vertex 1, we had this path to reach 2 and the distance was 6. But if we go via 1, we can reach from 0 to 2 in distance 3 minus 2, 1. Which is why this distance is 1, and we are indicating that to reach from 0 to 2 we go via 1. So this is true. Is 15 greater than 3 plus infinity? No. So now we increment our I by 1 and repeat the same process for j from 0 to 3. Is infinity greater than 0 plus infinity? No. Is 0 greater than 0 plus 0? No. Is minus 2 greater than 0 minus 2? No. Is infinity greater than 0 plus infinity? No. Then we're going to come here, I equal to 2, repeat the same process, no, no, 0 greater than no, 2 greater than infinity plus infinity, no. And finally, for I equal to 3, we again repeat j0 to 3. Is 1 greater than 4 plus infinity? No. Is 4 greater than 4 plus 0? No. Is 7 greater than 4 minus 2? Yes. 7 is greater than 4 minus 2. So what we are going to do is, we are going to go to 3, 2, 3, 2, and here we are going to set the value 4 minus 2, 2. So this value now becomes 2. And then we are going to go to 3, 2 and set this value to be whatever is the value at 1, 2. Value at 1, 2 is 1, so this value becomes 1. So again, basically, we found a shorter distance to reach. We found a shorter distance to reach 2 from 3. So before we were taking this distance via 3 to 0 to 2, but now we found a shorter distance, which is 3 to 0 to 1 to 2, which is what we are reflecting here and here. So next, let's check the last one. Is 3, 3 greater than 3, 1 plus 1, 3? No. So 4 plus 0 greater than 4 plus infinity? No. So now we are done with k equal to 1. So next, what we are going to do is we are going to increment by k by 1 more and repeat the same process. So let's do that quickly. So repeating the process for k equal to 2, is 0 greater than 1 plus infinity? No. Is 3 greater than 1 plus infinity? No. Is 1 greater than 1 plus 0? No. Is 15 greater than 1 plus 2? Yes, 15 is greater than 1 plus 2. So we go to 0 to 3, 15, set this value to be 1 plus 2, which is 3. And then we go to 0 to 3 and set this value to be path of 2, 3. So path of 2, 3 is 2. So set this value to be 2. So path of ij becomes path of kj. So basically whatever is at 2, 3 comes at 0 to 3. Then moving on for I equal to 1, is infinity greater than minus 2 plus infinity? No. This infinity indicates that there is no path from 0 to 2, which means that you cannot use this edge. So you cannot use 2 as an intermediate between 1 and 0. Is 1 greater than minus 2 plus infinity? No. Is minus 2 greater than minus 2 plus 0? No. Is infinity greater than minus 2 plus 2? Yes, infinity is greater. So we go to 1, 3. So we go to 1, 3. Set this value to be 0. And then we go to 1, 3 and set this value to be whatever is at 2, 3. So 2, 3 is again 2. So this becomes 2. So what happened was, before there was no path between 1 to 3. And now that we are going through 2, there is a path between 1 to 3 and the distance is 0. Next, let's move on for I equal to 2. Is infinity greater than 0 plus infinity? No. Is infinity greater than 0 plus infinity? No. Is 0 greater than 0 plus 0? No. Is 2 greater than 0 plus 2? No. Finally, for I equal to 3, is 1 greater than 2 plus infinity? No. Is 4 greater than 2 plus infinity? No. Is 2 greater than 2 plus 0? No. Is 0 greater than 2 plus 0? No. So this is how it looks for k equal to 2 iteration. So next, finally, let's do the k equal to 3 iteration. So repeating this process for k equal to 3 and checking for every pair of vertices, is there going to be a shorter path going via 3 or not? So 0 is not greater than 3 to 1, 3 is not greater than 3 plus 4, 1 is not greater than 3 plus 2, and 3 is not greater than 3 plus 0. Infinity is greater than 0 plus 1. So we go to 1 to 0, 1 to 0 and set this value to be 0 plus 1, which is 1. And then we go to 1 to 0 here and set this value to be whatever is at the value 3, 0. So the value at 3, 0 is 3, so this value becomes 3. 0 is not greater than 0 plus 4, minus 2 is not greater than 0 plus 2, 0 is not greater than 0 plus 0. So for going I equal to 2, infinity is greater than 2 plus 1. So we go to 2, 0 and set this value to be 2 plus 1, which is 3. And then we go to 2, 0 in this path matrix and set this value to be whatever is at 3, 0. So at 3, 0 we have 3. So this value becomes 3. Infinity is greater than 2 plus 4, yes. So we again go to 2, 1 and set this value to be 6. And we go to 2, 1 and set this value to be whatever is at 3, 1. So at 3, 1 we have value 0, so this becomes 0. 0 plus 2 is not, and 2 plus 2 is not greater than 0. 2 is not greater than 2 plus 0. Finally, for I equal to 3, 1 is not greater than 1 plus 0, 4 is not greater than 0 plus 4, 2 is not greater than this, and this is not greater than this. So this is it. This is our shortest distance matrix. So for example, the shortest distance between 0 to 3 is 3, and the shortest distance between say 3 to 2 is 2. So let's see how we are going to construct the path. So let's say I was trying to construct what is the shortest path between 0 to 3. So we are looking for the shortest path between 0 to 3. So first we go into this path matrix, go to 3, see what value is there. So this value is going to be right before 3. So we are reaching 3 via 2. Then we go to 0 to 2 because this value is 2. So we go to 0 to 2 and this value is going to be right. So this value is 1. So 1 is going to be right before 2. And then we go to 0 to 1 and we found this source value. So this is the path we reached 3 via 0. So 0 to 1, 1 to 2 and 2 to 3. And the distance here is 3 minus 2, 1 plus 2. 3 minus 2 is 1 plus 2 is 3. And that is the distance between 0 to 3. Let's look at another example. Let's see what is the minimum path from 3 to 2. So you go to 3 to 2. So 3 to 2 is 1. So we are looking for minimum path between 3 to 2. So you go to 3 to 2. So this value is 1. So 1 is going to be right before 2. Then you go to 3 to 1. So this value is 0. So 0 is going to be right before 1. And then you go to 3 to 0. And this value is 3, which is our source. So to go to 3 to 2, you go to 0. Then you go to 1. And then you go to 2. And the distance here is going to be 1 plus 3, 4 minus 2, 2. And that is the distance between 3 to 2, 2. So the time complexity for this algorithm is very easy to calculate. It's O of V cube. So as I said, we are repeating this. We have 3 for loops. As we saw, we have 3 for loops. And for every for loop, we are doing this work. So the total time complexity O of V cube, and the space complexity is O of V square. Finally, if you want to check if there is a negative weight cycle or not in the graph, what will happen is if you apply the same algorithm, if the values along the diagonal becomes negative, it means that there is a negative weight cycle in the graph. In this example, none of the values change from 0, which means that there is no negative weight cycle in this graph. But if there was a negative weight cycle, these values would have become would have become a negative number, which would tell us that there is a negative weight cycle in the graph. So finally, let's look at the code for this algorithm.
Function is all pair shortest path. It takes in a distance matrix where distance matrix ij is the distance of vertex I to vertex j. If there is no path from I to j, then the distance matrix will store a value infinity. Then we initialize 2 other matrices, distance and path, where distance is going to store the minimum distance of every vertex from every other vertex in the graph, and path is going to be useful to regenerate the minimum distance path from one vertex to another vertex. We iterate through the distance matrix and set the value of distance ij to be distance matrix ij, and if distance matrix ij is not infinity and I is not j, then path ij becomes I. Otherwise, path ij becomes -1, indicating that currently there is no path from I to j. Then, as we discussed in the video, we have these 3 for loops, I, j, and k, all going from 0 to the total number of vertices in the graph. If distance ik is infinity or distance kj is infinity, which means that there is no path from I to k or k to j, then we continue. Otherwise, if distance ij is greater than distance ik plus distance kj, then distance ij becomes distance ik plus distance kj, and path ij becomes path kj, again as we discussed before in the video. After we are done doing this for loop, distance ij stores the minimum distance from every vertex to every other vertex. Once we are done with the for loop, we are going to check if there is no negative weight cycle in the graph. To do that, we again iterate through the distance matrix diagonally and see if any of the diagonal value is negative. If any of the diagonal value is negative, then it means that there is a negative weight cycle in the graph, and then we throw this exception. Otherwise, we just return the distance matrix. Also, if you want to print the path from one vertex to another vertex, you can use this method. Print path. It takes in this path matrix, and here we are going to print the minimum distance path from vertex 3 to vertex 2. So here I is 3 and j is 2, and then we initialize a stack and add j into the stack, and then go into this while loop, and then j becomes path ij. If j is -1, it means that there is no path possible from I to j, which is when we return. Otherwise, we add j to the stack and keep going into this for loop till I becomes j, and as soon as I becomes j, we break out of the for loop and print contents of the stack, which is the path from I to j. So this is all I have to talk about Floyd Warshall all pair shortest path algorithm. The link to this code is in the description section of the video. Please like this video, share this video, comment on this video, like my Facebook page, and check out my GitHub link. Thanks again for watching this video.